Thank you. And thanks for the invitation to talk about something that I really find very exciting and interesting, and that's how we can improve our models. And to improve models, we need to find what it is that we want to prove, and we, in the Polar Prediction Project, or in YOPP, we defined early on, we knew sort of what was the problems in the models, and it's the parameterized processes in the models that have a harder time in the polar regions than elsewhere. And we know those things, but we don't really know how to best accelerate the model improvement. We need process observations that just Tanil was mentioning to really understand the processes that we want to model and to understand the issues and to do then the model, improve them. And I will just say that the process we are talking about here in this session will not be solved completely by high-resolution models. They will be improved, hopefully, but they will not be solved because these are really small-scale processes. So yesterday there was a lot of talk about when we started and where we were and so on, and I'd like to talk a little bit about the humans in this problem, if you say so. So I tried to depict it here. You have the model scientists working along there on the computer, sitting and thinking about how to do the numerics in the correct way and how to get the model to run very fast. And then you have the observational scientists that go out and put their instruments out on towers, and they want them to be as good as possible, and they know all the details about the instrumentation. And that's fine. That's what we worked with. And then we organized ourselves in the community. So there are modeling to comparison projects. Modeling to comparison projects use observations, kind of a lot of observations, but it's very seldom that the observationists really are in the room, really talking about it. So you compare models and you try to understand what's going wrong, and you use different kinds of models to be able to understand the process. And the observational scientists, they organize themselves in networks to discuss things there. And then we have a special category that are in the lower panel here that I call the expedition scientists that go in the field and do really, really detailed observations. And they usually have a couple of modeling groups along in that project that work very tightly to that. But the data that are generated in those is not really distributed to the wider community. So what we have been working on, and then there is all these kind of things, why that sort of organizes why we work in this way. And that's funding, that's publication, training, academic merit systems, etc., that sort of keep us in those different bubbles. So what we have tried here is to put everyone in the same room and to discuss it. So we're really co-designing the goal. The goal is already there. We know that we want to improve the process representation in models that we use for prediction in the polar regions. And then we try to define a common language to be able to really talk and really get into the details and really have a conversation on what we are trying to do. And we did that by defining a special file format. That doesn't sound very exciting, but you can talk a lot about that to really make sure that what we put in the files from the observations really matches something that we have in the model. And now I'm talking about the detailed processes here, and not like temperature is easy, but many other things are much harder to really get that. And then we need to have the conversation to understand what does the observations really tell us, how accurate are they, and so on. And if we modelers, I'm a modeler mostly, if I take an observation, I don't really know how uncertain it is and where and why I can use it and how. So that's why we want to have this conversation in the same room. And I will say that finally we are starting to get there. The pandemic has not been really helpful here because we haven't been able to be in one room. And I think there's very good opportunities now in the future if we can keep the world from having pandemic. So what we did here, and actually it started, with getting this conversation started, was a lunch between Tanil and myself in Boulder, where we had a very nice conversation of how we would do this. So in the brochure, you'll find a very detailed graphics trying to tell everything that we're trying to do in this, which we call the YOPPsiteMIP, that Tanil already sort of introduced. And the difference between this and other similar types of activities that we have going on is that we are trying to really get into the models. So we ask the modeling output to be on time step and on model levels. So we really are close to how they are parameterized in the models. And in the same way, we ask the observations to be on a very detailed level. So that's sort of the setup, and you will hear a lot more on this, and you'll hear a lot more about the common language that we defined, so the MDF data format that comes along with a number of different other tools as well. And you'll hear more about that in the YOPPsiteMIP session this afternoon, and also you can visit the visualization booth to see some of the tools that are working for this. So I said that we know what it is that we want to do. So what do we learn by having this? Well, if we take one station where we have lots of observations, and I picked Sodankylä here, and we look at all the forecasts that we have for the SOP1, which is in February, March 2018. You see that there is you see the mean error here and the standard deviation of the error, and you have a number of forecast models there. You see that all the models are doing basically the same thing. They have a diurnal cycle in their error. So the daytime error is smaller than the nighttime. It looks like there is a common bias here, so that we can really have a look here and work together on this. And then if we only had this site and only looked at this site, we would think that this is a pan-Arctic thing, that we have this kind of error. So let's see the other stations where we have observations from. And here it's the same scale on all of the figures, and it's all the different places we have all around the Arctic. And you can see, well, there are maybe one or two other sites that has this diurnal cycle problem, but not the others. They have other problems, and there the models are diverging even more. So this gives us a better handle on what's wrong in the model, and it will also give us a better handle on when we improve something, that we can test it in many more locations to see if those locations also are improved, if we do improvements. So there will be more on this talk later on this morning by Johnny Day on what we have found and what we learned so far from doing this modeling and comparison. So I said we know what goes wrong in the model, but but we should test and we should try out what's going on wrong in the model. And I think something that hasn't been looked at so much is the vertical structure of our models. And the permutations that we put in our models, the cloud formation, the turbulence, the radiation, all of these feed on gradients that we have in the vertical. So I think that we should look into what is the structure of the vertical profiles, and how does that affect what we have parameterized, and that in turn then affects the energy exchange with the surface. So this is an example where we're using the Odin drift station in 2018. So that's one of the endorsed projects, and it was during the SOP2. You can see that the forecast length here, you have the temperature in the top and the moisture. And you can see that there is a very clear, there is a very small initial error, and that's because the soundings that were made from this expedition, they went down the GTS and were used in the assimilation, so the first profile is fine. But then you see that very rapidly you develop an error, and that's almost constant with time after that. It's too warm in the lowest levels. Notice that there is a logarithmic vertical axis here, and then it's too cold. And the specific humidity follows that. It's too moist near the surface and too dry further up. The winds look surprisingly good, and we can't use the soundings for the winds in the lower part, so that's why it's blocked out there. But the winds in the wind direction look very good. And that's a bit puzzling to me. How can the winds be so good when the thermal structure is not? So that's something that maybe we should try to focus a little bit more on as well. So then we look at the detailed observations that we have for the clouds, and this is just one example then that we can see, okay, in that layer that we had this cold and dry bias, that's where we have the clouds, and we have too many clouds in the model. So maybe there is a connection here, that's the reason. So we need to look at this in combination. So I think we need to expose our models to these detailed observations to find out when and where and how it goes wrong. And then the work comes then to how to do it. And I just wanted to show this, another illustration here as well, that when we think about the polar regions, especially about the Arctic, we think about the Arctic inversion. And we see that it's increasing, and we see that very clearly if we do a monthly mean average. But if we look at the instantaneous profiles, when when we have an Arctic inversion all the way to the surface. But many times we have a near-neutral close to the surface, or even a convective profile, which means that the fluxes, and you see the observations from Mosaic and from Shiba here from a paper and a presentation that will be given later by Amy Solomon, that we see that there are both fluxes up and down, even in the winter time and in the high Arctic over the sea ice. So we need to be able to really look at the structure close to the surface, because that's what's determining the heat fluxes and not the overall monthly mean. So looking into more of these details, and we know that from research expeditions and detailed observations that we have at the super sites, we know that there is a lot of structure. You see the soundings and you see the remote sensing of cloud liquid, and then the potential temperature from the soundings there, and you can see that there are several layers, and you have the clouds there affecting, you have turbulence in the clouds, and if you do statistics on it, you can see that for this time period, which was the ASCOS expedition, which also was a drift part of that, of a month or so, you can see that the statistics shows that it's near neutral towards the surface in 91% of the times and stable only 9%. And it's different in summer and winter, and we have much more observations and much more knowledge what's going on in the polar regions in the summer than we have in the winter. But we have this great resource now with the Mosaic that we should make use of to try to understand this even better. You can also see there is an estimate from the process of observations of how much turbulence you have there. So next I want to talk a little bit more about the ongoing and planned MIP activities that we have. I don't think we have really agreed on how we should pronounce this extra I in the MIAP, but that's how it's, that I guess will evolve. So you already maybe heard a talk yesterday by Felix Pitan about how you can use global climate models and how you can do nudge simulations to be able to do a one-to-one comparison at that time. And we had this, and I'm also sort of giving a preview here that you will have the chance to look into and listen to Amy Solomon's presentation on how the numerical weather prediction models are doing during the polar night period of Mosaic. And I will next also talk a little more about the YOPP targeted observing period, which is something that we are analyzing quite in detail right now and see if we can use it to understand more of the models and using it for some community activities of looking into the forecast models and climate models in more detail about what's going on when we have the air transported from south to north and from north to south. So we have here this period in April that we have named then the targeted observing period. We had a collaboration with the Mosaic expedition, which was done in the middle of the Arctic at that time. And we were looking very carefully at the weather forecasts, and we had agreed with a number of sounding stations that we would release extra soundings if there was an interesting period coming. I must say that the Mosaic year was really, really boring there in the spring there because there was no meridional transport at all for a very long time, and then this event happened in April, and we were managing to get some extra soundings and some extra activities going on there. And this was really a big change from the very cold start, where you see that the temperatures are like minus 30 degrees, and then you have the first pulse of very warm air coming there, and then a bit of a colder, and then a second pulse where we almost reached melt at the Mosaic site. And you can also see in that we have the reanalysis temperature there. And that was also discussed yesterday. I mean, we know that the reanalysis temperature in wintertime is not very good, and you can see that clearly that it's too warm when it's cold, and it's too cold when it's warm, and it transfers to between those states with not the same speed, and that's because of the limited, the very simplified description of the sea ice in the reanalysis. Hopefully the next generation of reanalysis will do a much better job of that we can have a coupled reanalysis. So what we've done here is that we have calculated back trajectories using Lagrange in the ERA5 fields, And I'm happy to see that the wind speeds are very closely aligned here, so we can hopefully trust the circulation in the reanalysis, even though the thermal structure is not perfect, and to study what happens with the air mass when it goes from south there. There's also another expedition or experiment that was carried on at the same time, which is called COMBL, which was focusing on cold air outbreak, which is also something which was done in collaboration with the MOSAIC campaign. So this is the circulation situation at the first pulse in the upper row, and then the second pulse in the lower panel. So the first pulse of warm air was from the Norwegian coast. So it passed over this COMBL site, where we have lots of detailed observations. It almost passes over Ny-Ålesund and then reaches the Polarstern and the MOSAIC site. And it's interesting because trajectories usually they go in all kind of directions, but for those cases, they actually line up very nicely from almost 500 hectopascal and down to the surface. The air is going in the same corridor, which makes it a very interesting case then to try to study in a Lagrangian framework and see what the local processes are doing there. The 19th of April, the air mass is going very rapidly from south, and then, as I said before, the surface is almost starting to melt at that point. The real melt doesn't start until very much later, but this is really something that preconditions the ice and helps it get into the spring and melting. So I'm talking a lot about the energy that is coming from the atmosphere down to the surface, because that's the atmosphere's contribution to the sea ice evolution. And that was both done in the thermodynamic point of view, but also for the winds, because this is very windy situations as well. And you can see the moisture coming in there. And maybe I didn't tell you before, but the two figures here, the before and the second, you can see how the whole temperature of the whole Arctic changed before these events and then after. The color shading goes much more to the warmer temperatures there. So let's have a look what happens along these trajectories. So this is the trajectory arriving to Polarstern on the 16th of April at noon. And we've started the calculations there at 800 hectopascal. We are following that parcel, and you can see that with the stars, how it's moving a little bit in the vertical direction, but not a lot. And we're following that, and then we look at the column above and below from that level, where we have the trajectory. And you can also see the diagnosed boundary layer height, which you see there, and in the bottom you see the terrain, so you can see a little bit of the Norwegian coast when it goes off the shore there, and then it goes all the way over Svalbard, and then it reaches Polarstern when the zero. If you look at the humidity panel, you can see where it comes over the sea ice, which is denoted by the stars at the surface. So following this trajectory, you can see that there is warm air in the lower part from below like 2 kilometers. It's much warmer and it's much moister, and it picks up moisture when it goes along this trajectory. And you can also see the liquid clouds in the black contour lines, and then there are ice clouds as well. And you can see the vertical velocity movements in the temperature as well. So this is a way of looking at the Lagrangian transformation of the air mass, what happens with it when it picks up the moisture along the way, and then when it gets in over the ice, you have the creation of this low-level cloud, and the low-level cloud will have a big impact on the energy budget at the surface, the low-level liquid cloud there. I didn't tell you before, but the first part of the pulse on the second one actually goes over Greenland. And then when it goes over Greenland, you have a totally different evolution, of course, because then it has to go over this 3,000 high block there. So you can see that it's very warm in the south, 48 hours before arriving at the Polarstern. It goes across Greenland and goes up, and you form lots of clouds and lots of precipitation. And then on the other side, so you'll have a Föhn effect here that's much drier and warmer. And here you can see that the warmer air is at height, and it's at about 1.5 kilometers and not so much close to the surface. But there is still a cloud forming over the sea ice there, the liquid cloud. And here it's interesting to know, is it the warm air at the top that is making the energy budget at the surface going positive? Or is it the tiny little cloud that is formed there? And how important is that to capture in the model? And then finally, then when we have this straight, very fast advection from south, from Iceland and going north, we can see that we have very warm air at both near the surface and above. And you can see the cooling when you get the cloud formed, and it goes along the Greenland coast, along over the sea ice for quite some time before it gets to Polarstern. And you have a really solid liquid cloud there. So combining the Eulerian perspective of looking at the certain stations and trying to understand the models and what's going on there, and following the air mass along a trajectory and seeing what's happening in the model and how our parameterizations are creating the clouds and the radiative cooling and so on, is like a complementary framework to try to understand what's going on in these meridional transports. So I've said that we already know. We have a complex environment, we have many small-scale processes, and we know the challenges that we have with the representation of them. We know that the stable boundary layer is tricky. We know that it's very hard to get the mixed phase clouds in the right place and with the right phase. We do know about them, but we don't know enough about when and how these issues appear in the model. And that's why we need to have this confrontation with detailed observations to really understand when and why does it go wrong. And we know also that we have a lot of compensating biases in our models, but we don't know really when they happen and why. So I think we need to really improve models. We need to know these details and really dig into them to understand it. And I also wanted to just show you that we have created and there is also a lot of things happening in the interaction with the atmosphere and the sea ice and below as well. And for that, we have the mosaic observations, which actually goes down into the ice and snow and ocean, where we can compare with things going on there as well as we develop the coupled models. So we have a coupled single column model where you can go into detail and study this as well under controlled advection, situations, or we can also do it in Lagrangian. And I was to point there will be a talk by my PhD student Mikhail Karalis about this first attempt to try to do that. I also wanted to touch on that the models that we have in the processes that we are describing in the weather prediction models are the same that we have in the climate models. So here is a really great opportunity to really work together to try to understand how we should do this in the best way. And I just wanted to point to this paper that shows that the Arctic amplification that we've said for so many years, that it's twice as, the Arctic warming is twice as fast as as in the global value. And this study shows that there is even maybe 4 times or even more than that in the region. And on the right-hand side, you see some estimates from climate models, both generation CMIP5 and CMIP6, and none of them can capture the really rapid warming that we've seen the last 20, 30 years or so. So, and then we also know that, well, the observations that are based on this long time series is not the greatest, but still there seems to be a lot of things that are not done right in the climate models. There is a lot more information that is going on that you will see here later today if you go to the Mosaic, or the YOPPsiteMIP session, and tomorrow I think there is the Mosaic. But there's a lot of things going on and a lot of papers that are written now, and that's the reason why we wanted to extend these activities at least for 1 more year to be able to report on everything that's going on. And as my summary here, I wanted to say to you that the YOPPsiteMIP have gained substantial momentum despite the pandemic. And then it looked like I wanted to say something more, but I haven't finished that, so let's not talk about that. And the concept with the MDF file format, that's sort of the common language we have with its toolkits, is used for other data as well beyond the SOPs that we started with. And most notably, the Mosaic has a MODF file as well, and there will be more. And I think this concept can be really exported and transported to other sites, because global models are global. We need to know how it works everywhere, not just in the polar regions. Next is to get some stations of observations for the southern hemisphere, and I think there is also a possibility for the third pole regions. We already did that when we started this project, so we have model output for the third pole regions, but not observations. But for this to happen, we need champions. We need people that knows these observations and wants to get involved. And then we talked about these polar process MIIPs, so the comparison and improvement. And we already have some plans. We would want to continue the analysis of the weather forecast model that we started from Mosaic and going into more details. I talked about the TOP, which is a great case, I think, to look into more detail about warm air advection to the Arctic. And then we have another initiative that is also ongoing that is based on the COML data and Mosaic that is going the other way, so it's a cold air outbreak. And that's co-organized with GAS, and we're also keeping contact with Mosaic and the planning of the modeling there. And then more community activities can be discussed and can be launched, but we need to know what the community wants then. What is it that we should focus on? What next? And we will have a breakout session and a brainstorming session there, what we would like to hear your opinion. So I hope you will think about that during the day so we can see and gather some interesting cases and things that we can do in the future. We need to continue improving our models, and especially the processes, I think. Thank you.
Thanks, Gunilla. So, some question in the room? Yes?
I have one question. In a case study, you show a very interesting scatter plot linking the wind and turbulent heat flux. And in the same case, you also show that at the surface, the simulation is more or less too moist. And also there's sun changes in the cloud. So we may expect to see more radiation change, heat flux change in that case, because too moist will directly affect the long-wave radiation. So we may see more long-wave, and cloud will directly affect the short-wave radiation. So maybe to complete the surface energy budget and also to help understand surface temperature anomaly, it may be useful to check that as well. Thank you.
Yes, so I cited a paper in that, on that plot, and there is a lot of discussions also. We are looking at the vertical structure in combination with the surface energy budget terms to see how they are affected. So that's definitely the case. But there is a puzzling still. We don't really understand what's going on in the model and why we get it too warm there, because that's probably linked to all the permutations and how they are working.